Torque and static equilibrium. Torque. So torque looks at when you apply a force to something that is moving in a circular motion. So force with the rotation. So let's say you have some sort of a wrench and you're going to use that to tighten or loosen a bolt. And when you apply a force to the wrench, let's say you apply a force downward, the wrench will start to move in a clockwise direction, rotational direction. And the only other thing I'm interested in is how far away I am from the pivot point of rotation when I'm applying my force. So the distance of my pivot point to the force would be from here to where I'm applying my force, and we're going to call that distance r. If I know the distance away from the pivot point, and I know the force that I'm applying to the tool I'm using to rotate, then I can find the torque. So torque, using the Greek letter tau, is equal to the length of the lever arm, and that's the distance from the pivot point to where you're applying your force, multiplied by the perpendicular force. The SI unit for torque then would be a meter multiplied by a newton. Notice that that is different from a newton multiplied by a meter. Usually we say a newton meter is a unit we use for energy. If you ever see a unit of a meter times a newton, that means we're talking about torque. Let's do an example of finding a net torque on a wheel. So we have a wheel and there's going to be a force applied at somewhere in the center of the wheel, let's say down, and we'll call that F sub A. And there's also some other force acting in a different spot on the wheel, say somewhere on the outside at an angle here. We'll call that F sub B. And we have an angle here, theta. Now the wheel is going to rotate around its center, so there is a distance away from the pivot point for FA. We're going to call that R sub A right here, and there is a distance from the center of the wheel we'll call R sub B, which is right there. The forces in this problem, F sub B and F sub A, will be equal, but if you notice their distance away from the pivot points are different. So R sub A is a little bit shorter than R sub B. Okay, so looking at our given values, F sub B and F sub A are both have a magnitude of 50 newtons. The length of the lever arm for force A is 0.30 meters, and the length for the lever arm of R sub B is 0.50 meters. Another thing I haven't done yet is I need to assign direction, so we can make to the right plus X, up plus Y. And since we're talking about rotations, we also need to assign a direction for clockwise or counterclockwise. So I'm going to say clockwise is positive. Sometimes your textbook calls counterclockwise positive, so you really need to pay attention to your direction. Okay, so what I would like you to do in this problem is to find the net torque. What is the net torque? And so what we're going to do to find the net torque is we're going to add the torque because of force A plus the torque because of force B. Using the formula for torque then, the torque for A is going to be the length of the lever arm for A multiplied by the perpendicular force, the force A, plus we're going to have the length of the lever arm with force B multiplied by the perpendicular part of force B. And when you go back to the diagram, we also need to look at direction. So when we look at force A, if you look closely, you can see if force A starts to make the disk rotate, it's going to rotate counterclockwise. So the torque I would get from that would be negative. So I'm going to put a negative in front of that. And all of this added together will be the net torque. Okay, I want to talk about this perpendicular value of F sub B. Let's go back up to the drawing. If you look at F sub B, in blue, F sub B is acting at an angle, and I only want the perpendicular component to R sub B. So the perpendicular component to R sub B, I'm drawing in green here, I'm going to call that F sub Bx. This is the component of F sub B that is perpendicular to R sub B. And so that is what I'm going to use in the formula. And using a little bit of trig, hopefully we can figure out what Fbx is. Okay, let's start plugging in some numbers. So R sub A is 0.3 meters. F sub A, which is perpendicular to R sub A, looking back up at the drawing, we're just going to multiply that by F sub A, which was 50 newtons. We're going to add that to R sub B, which is 0.5 meters. And we're going to multiply that by the perpendicular component of F sub B, which we talked about earlier as my green component, the Fbx. That's going to be F sub B cosine of the angle. Let's call that angle 30 degrees. And now we're ready just to solve. So plugging in 50 for F sub B and solving, we should get a net torque of a positive 6.7 meters times a newton. The positive value for the 6.7 means that the direction is clockwise. You could also put a comma here and write clockwise to the right. And then we'll put a little box around it. Okay, now we're going to talk about static equilibrium. For static equilibrium, there are basically two conditions, and that is the net force acting on an object is 0, and the net torque acting on an object is 0. That's it. The first example I'd like to show you using static equilibrium is called the beam problem. You have some sort of wall and there is a beam coming out from the wall. The beam is held up because there's some sort of cable holding it up to the wall. And perhaps there's some sort of sign hanging down from the beam. And the beam itself is allowed to rotate, so there's some sort of hinge point, and the hinge point is going to be right at this point. So in fact, there's going to be a force from the hinge, I'm going to call it F sub h, right there. Drawing a free body diagram on the beam, there will also be a weight of the beam. If the mass of the beam is uniformly distributed, then the weight of the beam will act right at the center of the beam. I'm going to call that the mass of the beam times g. The sign itself has a weight acting on the beam down, and we're going to say the mass of the sign times g. There's also a force of tension acting on the beam from the cable. And lastly, there's going to be an angle that I'm interested in with the cable and the beam, and I'm going to call that theta. Assigning direction, we're going to make right positive, up positive, and I like to make clockwise positive. Writing out the givens, the length of the beam, which I'm going to call r, is 2.20 meters. The mass of the beam is 25 kilograms. The angle of the cable and the beam is 30 degrees, and the mass of the sign is 28 kilograms. In this problem, I'd like you to find the net torque, or hang on just a second. Let's try that again. In this problem, I'd like you to find the force of tension acting on the beam. I'd like you to find the horizontal component of the hinge force and the vertical component of the hinge force. Now, in order to do this problem, we need to understand that the beam is in static equilibrium. In other words, the beam is not accelerating, its motion is not changing, and therefore we can apply the conditions that the net torque is 0 and also the net force is 0. So we're going to say that the net force in the x direction is 0, the net force in the y direction is 0, and the net torque is 0. I'd like to start by looking at the net torque acting on the beam. As you recall, torque is the length of a lever arm multiplied by the perpendicular force being applied to that. And this all has to do with a rotational motion. So there must be some sort of rotational motion and a pivot point on which an object is rotating. When we do a problem like this, we get to pick the point of rotation. And I would like to pick the point to be at the hinge in the diagram above. And so the first force that I'm interested in is the hinge force. And the distance away from the hinge force, which is the pivot point, so the distance away from the pivot point in this case is 0, because the pivot point is the hinge force. Now the next force acting on this beam is going to be the weight of the beam itself. So that's going to be M sub B G. And what is the perpendicular distance away from that? Well, that's going to be half the length of the beam. So that's going to be what I'm calling 1/2 the length of R, which I have in the given. Now, another thing I want to look at here is if this beam were to be allowed to rotate because of the weight of the beam itself, what direction would the beam rotate? And when I look at the diagram, I can see that the beam would rotate clockwise. So this value here in my equation should be positive because I defined clockwise as positive. Okay, let's look at the next torque. The next torque has to do with the force of the sign being applied to the beam. So that would be the weight of the sign multiplied by the perpendicular distance away from rotation, which is the whole length of the beam itself, so that's R. And again, the beam would rotate clockwise if the weight of the sign were allowed to rotate the beam. We have one more force to look at, and that is going to be the perpendicular force of tension that is acting on the beam. So as you see now, the force of tension itself is not acting perpendicular to the beam itself. So we need a component of the force of tension. And in green, I'm drawing it in the diagram here. We're going to call this F sub Ty. This is the force that is acting perpendicular to the length of the beam. So going back to my equation down here in green, I'm going to have the force of tension in the y direction, and I'm going to multiply that by the whole length of the beam, which is R. Now going back to the picture, if the force of tension in the y direction were allowed to make the beam rotate, what direction would the beam rotate in? And the answer is the beam would rotate counterclockwise. So I'm going to sneak in a little negative here, so we can fit that in the equation. Because this last torque value in my equation is negative because due to the force of tension in the y direction, the beam would rotate counterclockwise. Let's simplify this equation. So the net torque acting on this whole beam will be 0. We know that the hinge force times 0 is 0, so we can get rid of that term. We can also divide everything else by r, so all the r's are going to cancel. And so what I'm going to be left with is the weight of the beam, 1/2 of that, plus the weight of the sine, minus the force of tension in the y direction. So solving for F sub t, I get 793.8 newtons. Okay, now let's look at the sum of the forces in the x direction. There is a force because of the hinge in the x direction minus the force of tension in the x direction. Using static equilibrium rules, that's equal to 0. So Fh sub x is equal to Ft sub x, which is equal to Ft cosine of 30 degrees. So Fh sub x is equal to 687 newtons. Looking at the sum of the forces in the y direction, we will have a Fty minus the weight of the sine minus the weight of the beam plus the y hinge force, and that's all equal to 0. So my hinge force in the y direction will be m sub sg plus m sub bg minus the force of tension in the y direction, which is the force of tension sine of 30 degrees. So plugging in the numbers, we get 122.5 newtons. So for practice, page 220, number 24, out of your text for number 1. For number 2, I want you to try this problem. It's called the ladder problem. I have a ladder. It's propped up against a wall. The wall is frictionless, and so there is a force from the wall acting in this direction on the ladder. The ladder is also propped on the ground, and there is friction on the ground, so there's a force from the cement on the ground that acts in this direction, force from cement. There is also the weight of the ladder itself. The mass is evenly distributed, so the weight of the ladder is going to act at the center, and that's going to act right here. We'll call that mg. This is a right triangle here, or right angle. We have an angle here I'll call theta. We're going to make this length here 3 meters. We're going to make the vertical height 4 meters. So by using Pythagorean's theorem, you can find the length of the ladder. The mass of the ladder is 12 kilograms. Using the conditions for static equilibrium, I would like you to find the force of the cement acting on the ladder, and I would like you to find the force of the wall acting on the ladder. A hint is that the force of the cement acting on the ladder, you're going to need to use Pythagorean's theorem to find that. You're going to need to find an FCX and an FCY to find FC. And don't forget to also find the direction of F sub C. And just to recall, the conditions for static equilibrium are the total forces in the x direction are 0, the total forces in the y direction are 0, and the total net torque is 0. And I'll write the answer below. And lastly, there's a third problem here, which it will be very helpful if you check example 9-2 on page 228 before you attempt this problem. Have fun.